This is the fifth in a series of 8 chemistry labs on the fundamentals of biodiesel. In this lab, we will learn about transesterification of vegetable oil and alcohol to produce ethyl biodiesel. Written procedures and background information for all 8 labs is provided on the Biodiesel Education website. The process for making biodiesel, called transesterification, is a chemical reaction in which 1 mole of triglycerides, vegetable oil or animal fats, reacts with 3 moles of alcohol to produce 3 moles of ethyl esters, biodiesel, and 1 mole of glycerol, a coproduct. Although there is a 3-to-1 molar ratio of alcohol to oil to satisfy a complete reaction, a 6-to-1 molar ratio is usually used to drive the reaction to the product side. The excess alcohol that was not used in the reaction separates partly with the fuel and partly with the glycerol at the end of the process, and can be recovered and reused through a process of distillation. Typically, a strong base such as sodium hydroxide or potassium hydroxide is used as the catalyst, which normally would not be consumed during this reaction and would end up in the glycerol layer. A triglyceride is a molecule made up of 3 fatty acids attached to a glycerol backbone. The 3 fatty acids on each molecule could be the same or they could be different. The fatty acid makeup of the oil or fat is responsible for some of the properties found in the resulting biodiesel. The transesterification reaction will proceed quickly at first and eventually slow down as it reaches equilibrium. At this point, there will be some unreacted glycerides left in the biodiesel. It is possible to improve the quality by removing the glycerin that has settled out and to run another reaction, thus pushing the equilibrium point farther to the product side. For this lab, 1 reaction should be enough to get a good separation of the glycerin from the biodiesel. In this laboratory exercise, we will be making a small batch of biodiesel. To conduct the exercise, you will need a 125 milliliter and a 250 milliliter flask, all with stoppers, a 250 milliliter separatory funnel, a stirring hot plate and magnetic stir bar, thermometer, aluminum foil, and a weighing scale. For reagents, you will need 100 grams of vegetable oil, 20 grams of 100% ethanol, that is anhydrous, and 1 gram of potassium hydroxide for the catalyst. You will also need to prepare the database tables as shown here. The first step is to calculate the molecular weight of ethanol. It can be very difficult to calculate this molecular weight of a fat or oil, since they are made up of many different large molecules, triglycerides, each with different fatty acids attached. For this exercise, we will use a value of 877 grams per mole for canola. Since we are using 100 grams of oil, we can use the following relationship to calculate the ethanol needed for a 6-to-1 ratio of methanol moles to triglyceride moles. Following safe lab procedures, carefully weigh out 1 gram of potassium hydroxide into a 125 milliliter Erlenmeyer flask. Into this same flask, add the amount of ethanol you calculated. Add a stir bar, cover with aluminum foil, and place on a stirring hot plate. Mix until the potassium hydroxide is completely dissolved. Set this aside. Now weigh an empty 250 milliliter Erlenmeyer flask and record the weight in your data table. Into this same flask, weigh out about 100 grams of vegetable oil to be converted to biodiesel, and record the exact weight in the data table. Add a stir bar, put on a hot plate, and start to heat the oil to around 60 degrees Celsius. Once 60 degrees Celsius is reached, add the alcohol catalyst mixture to the oil in the flask and cover with a watch glass or aluminum foil to keep the alcohol vapors from escaping. Stir this mixture at a moderate level 60 minutes while holding the temperature at 60 degrees Celsius. After 60 minutes, stop heating and stirring and carefully transfer the mixture to a separatory funnel and allow it to cool down and separate for 20 minutes. Weigh a 125 milliliter flask and record the weight. Carefully remove the lower layer of glycerol from the bottom of the funnel into this pre-weighted flask. The upper layer is the biodiesel phase, and the separated lower layer is the crude glycerol with some catalyst in it. Weigh the flask with separated glycerol and record the net weight into the data table. Based on the crude glycerol weight, calculate the estimated biodiesel yield. Also, calculate the average molecular weight of the ethyl esters using the known molecular weights of oil, ethanol, and glycerol, with the relationship shown here. Thank you for watching the Transesterification of Vegetable Oil and Alcohol to Produce Ethyl Esters lab of the Fundamentals of Biodiesel. Please go to the Biodiesel Education website for a complete written transcript of this lab exercise.